It's all about flames, fluids, and materials research aboard the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to StationLIFE.
Houston on 2 for velocity calculation, assembly, steps 4, 5, and 4, 6. We're moving on to step 5.
You will go right now for that activity.
Copy. Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Welcome back. This month on StationLIFE, we're going to look at how the unique environment on board the International Space Station enables physical science research. Our space station is a laboratory unlike any on Earth. As we orbit in free fall around the planet, we have the opportunity to control gravity as a variable in our research. The pristine microgravity environment allows us to observe aspects of fundamental physics that aren't possible here on Earth. You see, gravity often masks or distorts subtle effects such as surface tension and diffusion. On ISS, these forces can be harnessed for a wide variety of physical science applications. So on today's program, we're going to look at how the lack of gravity affects the physical sciences of flames, fluids, and materials.
The International Space Station is the largest, most complex object ever assembled in space, and is clearly visible from Earth with nothing more than the naked eye. From end to end, the station is slightly longer than an American football field.
The biggest shock, I would say, the biggest impact that I had during my flight is the first time I looked out the window of the orbiter and saw the space station. It was huge. It was huge and shiny and beautiful. Looking at it and knowing that a man-made structure that big is actually up there.
The interior of this incredible structure is larger than a 5-bedroom house, with 2 baths, a gym, and a 360-degree bay window. The station's mass is almost 1 million pounds, and it contains about 32,000 cubic feet of living space. The space station functions as a microgravity and life sciences laboratory, a testbed for new technologies, and as a platform for both Earth and celestial observations. The complex is made up of multiple interconnected modules, grouped together at the center point of a 357-foot-long integrated truss structure. Power is generated through 4 giant solar arrays attached to the ends of the truss. The pressurized components include 3 laboratories: the U.S. Laboratory Module Destiny, the European Research Laboratory Columbus, and the Japanese Experiment Module Kibo. The Russian Service Module is the structural and functional center of the Russian segment of the station. It provides living quarters, communication systems, an exercise facility, and flight propulsion systems. Other Russian segments include the functional cargo block, 2 mini research modules, and a docking compartment. The Italian Space Agency provided a permanent multi-purpose module, which can host up to 16 additional racks containing equipment, experiments, and supplies. There are 3 modules called nodes that connect the elements of the station and provide berthing ports. The primary residential areas include the Russian Service Module and Node 3 Tranquility, which contains a bathroom for crew hygiene and exercise equipment, a treadmill, and a zero-G weightlifting device. The Quest airlock provides the capability for extravehicular activity, or EVAs. This is the module that provides the exit for spacewalking astronauts to go outside the station to work. The cupola is a small module designed for the observation of operations outside the space station. Similar to a bay window in a home on Earth, but with a 360-degree view, the cupola allows crew members to observe the approach of vehicles, as well as all robotic arm operations and spacewalks. The Canadian-built Space Station Robotic Arm is a larger version of the arm on the Space Shuttle and is used to move equipment and hardware around outside the station. The space station is the home of 6 full-time crew members and is made up of astronauts and cosmonauts from nations around the world. More than 200 people have visited so far, and at least another 120 will live there over the next decade.
When you're up there for 6 months, or in Scott Kelly's case, an entire year, it's really the working in space part that becomes kind of the thing you love the most. It's the thing that gets you through the days. You're working with these professionals on the ground, and a lot of them have spent their entire lives working on these science experiments, and here we are up there and we get to operate them, and it's really an honor to get to do that. And in many ways, those are some of my fondest memories of being in space. You get to work these experiments, and they're usually watching over your shoulder from the ground. And there was a lot of times where I would do something, whether it was fluids or with flame research, it really didn't matter. The investigator would just say, whoa, wait, do that again. That was incredible and totally unexpected. And that was what just made you smile big up there when hey, we've been flying in space a long, long time, but we are still doing research that has unexpected results every single day on the space station. And I really love that about being up there.
In microgravity, something as simple as a candle flame looks and behaves completely different than here on Earth. Scientists are studying combustion on the space station with the hopes to improve efficiency of fuels and reduce pollution. Isn't that cool? Fire, it is often said, is mankind's oldest chemistry experiment. For thousands of years, people have been mixing the oxygen-rich air of the Earth with an almost endless variety of fuels to produce a hot, luminous flame. There's an arc of learning about combustion that stretches from the earliest campfires of primitive humans to the most advanced automobiles racing down the superhighways of the 21st century. Engineers studying burning to produce better internal combustion engines. Chemists peer into flames looking for exotic reactions. Chefs experiment with fire to cook better food. You would think there's not much more to learn. When it comes to fire, flames are hard to understand because they're complicated. In an ordinary candle flame, thousands of chemical reactions take place. Hydrocarbon molecules from the wick are vaporized and cracked apart by heat. They combine with oxygen to produce light, heat, carbon dioxide, and water. Some of the hydrocarbon fragments form ring-shaped molecules called polycyclic aromatic hydrocarbons, and eventually soot. Soot particles can themselves burn or simply drift away as smoke. The familiar teardrop shape of the flame is an effect caused by gravity. Hot air rises and draws fresh, cool air behind it. This is called buoyancy and is what makes the flame shoot up and flicker. But what happens when you light a candle, say on the International Space Station? In microgravity, flames burn differently. They form little spheres. Space station flame balls turn out to be wonderful mini labs for combustion research. Unlike flames on Earth, which expand greedily when they need more fuel, flame balls let the oxygen come to them. Oxygen and fuel combine in a narrow zone at the surface of the sphere, not here and there throughout the flame. It's a much simpler system. Recently, on a space station experiment called FLEX, where scientists learn how to put out fires in microgravity, they noticed small droplets of heptane were burning inside the FLEX combustion chamber. As planned, the flames went out, but unexpectedly, the droplets of fuel continued burning. The flames are there, just too faint to see. These are cool flames. Ordinarily, visible fires burn at a high temperature between 2200 and 3100 degrees Fahrenheit. Heptane flame balls on the space station started out in this hot fire regime. But as the flame balls cooled and began to go out, a different kind of burning took over. Cool flames burn at the relatively low temperature of 400 to 1000 degrees Fahrenheit, and their chemistry is completely different. Normal flames produce soot, carbon dioxide, and water. Cool flames produce carbon monoxide and formaldehyde. Similar cool flames have been produced on Earth, but they flicker out almost immediately. On the space station, however, cool flames can burn for nearly a minute. There are practical implications of these results. For instance, they could lead to cleaner auto ignitions. One of the ideas that auto companies have worked on for years is HCCI, short for homogeneous charge compression ignition. In the automobile cylinder, instead of a spark, there would be a gentler, less polluting combustion process throughout the entire chamber.
The chemistry of HCCI involves cool flame chemistry. The extra control we get from the steady state burning on the space station will give us more accurate chemistry values for this type of research.
I'm just getting my safety cutter on the other side of my IDA back here.
Copy, Terry.
A lot easier without the pool stanchion.
Absolutely, yeah. And it's just like in the pool instead of that, with the exception of that big blue planet down there.
Exactly.
As the International Space Station flies 257 statute miles over the coast of Chile, Terry Virts in the initial moments of his first spacewalk.
As you can see, combustion research on ISS can have tremendous benefits back here on Earth. We also want to better understand the behavior of flames in spacecraft to guide strategies for extinguishing accidental fires. The new SAPPHIRE experiment is going to be hot.
SAPPHIRE is contained inside a 2-foot by 3-foot by 4-foot box that consists of an avionics bay containing the computer and instrumentation and a flow duct which holds the material to be burned. This will be carried aboard Orbital's Cygnus spacecraft during a scheduled cargo resupply mission to the International Space Station. Once at the station, SAPPHIRE will remain on Cygnus until all the supplies are offloaded by the crew of astronauts. Once supplies are offloaded and replaced with trash from the ISS, Cygnus will depart. Once reaching a safe distance from the station, NASA Glenn engineers working from Orbital's Mission Control Center in Dulles, Virginia, will remotely turn on the experiment. Cygnus will then be put into free drift, while the SAPPHIRE experiment is conducted up to 2.5 hours. The experiment's sensors and video cameras are designed to capture valuable data and imagery, documenting large-scale flame spread and material flammability limits. At the conclusion of the SAPPHIRE experiment, the Cygnus vehicle will remain in orbit, while the data captured is downlinked to several ground stations around the globe and transferred to NASA Glenn's scientists and engineers in Cleveland. When downlink is complete, Cygnus will then begin its re-entry through the Earth's atmosphere, where it will burn up over the Pacific Ocean.
Serious. What are we going to do today?
Well, today, first I have to start off by saying that today I'm with someone who needs no introduction, because you've all seen him before. He's the guy we love, Dr. Don Pettit. Welcome to Station Life.
It's good to be back on station. I guess we're really not back on station, but it's good to be here on Station Life.
Thank you, yes. And I am just beyond excited today because Don is not only one of the most fantastic astronauts ever, he's like one of my favorite people. So this is a landmark event in Station Life history that we have with us.
And we both studied chemistry in college.
And look at what he's wearing.
See, I've got my periodic table shirt on.
Yes.
Okay.
Coffee cup.
Coffee cups. So,
Space cup.
So we have the first generation, the second generation, and both of these have been on station. This is a food-grade plastic, so it meets flight safety and all of that. Here is a variant of the second generation.
What's that for?
Well, this is for Earth, because this is slip cast out of porcelain, and it has this really cool, smooth look that shows off the form and the beauty of the design of this. Yeah, but porcelain is breakable. You can make these sharp shards, and in a weightless environment, they could float around. They could get in your eye, or even worse, you could inhale one of these aids and get them in your lungs. So we can't take the porcelain ones on orbit, but they're really cool looking, and we can use them here on Earth.
Awesome. Shall we?
Shall we? Notice your nose goes right in the cup,
Right in
and
here.
you get this burst of
Java.
Java,
Yes.
Yeah, that's a good mix of cream.
You like that?
Yeah. And let me read what it says. It says Space Cup, and that's the official name of this. That's the op-nom for the space station, the official sanctioned space station experiment. It's the name of the experiment is capillary beverage.
Capillary beverage.
And the name of the cup is Space Cup. And then there are the words on it. It says Capillary Experiments International Space Station.
That is so
Skeletonized
awesome.
NASA meatball.
This would be a collector's item for sure.
I was thinking, Trace,
Makes me want to go back up there.
that if you look at everything that I will have accomplished in my life, in 400 years, nobody even remember that I even walked the surface of Earth or floated around in space. However, I predict that in 400 years, people living and working in space will be drinking, sipping, and toasting out of cups based on my design.
Yes. And you'll be legend. You are legend. What am I talking about?
They won't
Present
remember
tense, you are
anything like
legend.
that. Like, do you remember who invented fire? Let's see, and who invented the wheel?
No.
You see, nobody needs to remember who did these things. The important thing is you got to know how to build a wheel, and you got to know how to control fire, and then your civilization can take off. And in space, you don't need to remember who messed with the surface chemistry to make these, but you need to know that how to make them, and that you can use them, and it will help build the civilized nature of human beings interacting with each other when you're in a weightless environment.
Well, Don, I've just had so much fun having you on StationLIFE and sharing your invention and your passion for science and coffee and bringing people together. And I think you've done that in a number of ways, but none so illustrative as the space cup.
I call this a wrap. Huh?
Me too.
A normal coffee cup or a normal open container just simply won't work in a weightless environment because the liquid will be in the bottom of the cup and you tip it up and it still stays in the bottom of the cup. If you move it around too violently, it'll all splash out and make a big mess. So we end up having to drink our beverages through a straw from a bag. Makes you feel like you're a big insect sucking the juices from another insect. I wanted to see if I could figure out a way to have an open container cup in a weightless environment which would allow you to drink your tea and your coffee in a manner that's commensurate with how people drink their beverages on Earth. Taking some of my surface chemistry that I learned in college, I devised a cup with a special shape. The cross-section looks kind of like an airplane wing where it has a cusp, and the cusp will allow channel flow so the liquid from the bottom of the cup will float up and just park itself right next to the rim, and then you can drink it. And it allows a crew to share a communal beverage. You could share tea. Maybe you just come in from doing a spacewalk or something and you want to celebrate a little bit. If you have a real cup, an open container, it's so ingrained in human beings, it's so ingrained in culture, it adds back the dimension of what it's like to be a human being in a civilized way.
Okay, flames and fluids are acting a little differently. But that's not all. Take a look at how microgravity affects colloids, magnetic fluids, and smart materials.
If you have a smartphone, take it out and run your fingers along the glass surface. It's cool to the touch, incredibly thin and strong, and almost impervious to scratching. You're now in contact with a smart material. Smart materials don't occur naturally. Instead, they're designed by engineers working at the molecular level to produce substances made to order for futuristic applications. The Corning Gorilla Glass that overlays the displays of many smartphones is a great example. It gets its toughness in part from fat potassium ions stuffed into the empty spaces between old-fashioned glass molecules. When the molten glass cools during manufacturing, dense to packed molecules solidify into a transparent armor that gives Gorilla Glass its extraordinary properties. Around the world, designers are working on other smart materials, such as alloys that can change shape on demand, plastics that heal themselves when ruptured, and fluids that obey magnetic commands to flow or stiffen under computer control. One of the greatest challenges in creating a smart material is arranging the molecules. They're so small. We want to create a new class of materials beyond smart. We need genius materials, materials that arrange themselves. The research to accomplish this is already underway on the International Space Station. Dr. First is the principal investigator of an experiment called In Space 3. In the microgravity of Earth orbit, vials of fluid mixed with very small colloidal particles, about 1/millionth of a meter in diameter, are exposed to magnetic fields. Magnetism can be switched on and off again very rapidly. This jostles the particles, causing them to bump together and self-assemble into microscopic structures. These structures can be very difficult to predict, even using cutting-edge models running on supercomputers. Astronauts enjoy watching this process in action through microscopes. Because the samples are backlit by a green lamp, they sometimes call it the green blob experiment. First recently won an award from the American Astronautical Society for his work on In Space 3. Just by toggling a magnetic field, we're learning how to take many kinds of microscopic building blocks and get them to spontaneously form interesting structures. Recently, observers have seen the colloidal particles forming long fibrous chains. First speculates that these could lead to materials that conduct heat or electricity in only one direction. The experiment has also yielded crystalline structures that the team is just beginning to investigate. The fluids underlying these tests are themselves very smart. They're called magnetorheological, or MR fluids, because they harden or change shape when they feel a magnetic field. If you own a sports or luxury car, you might have MR fluids in your shock absorbers. The stiffness of magnetic shocks can be electronically adjusted thousands of times per second, providing a remarkably smooth ride. Similar but more powerful devices have been installed at Japan's National Museum of Emerging Science and China's Dongting Lake Bridge. They're there to counteract vibrations caused by earthquakes and gusts of wind. Some researchers have speculated that MR fluids might one day flow through the actuators and hydraulic dampers of robots, moving artificial joints and limbs in lifelike fashion. Scientists and researchers are using these fluids as a laboratory for studying self-assembly. MR fluids are, by definition, responsive to the magnetic nudging that sets self-assembly in motion. Furthermore, in space, the particles don't sediment out due to gravity. We can study the full 3D evolution of the material. Varying the shape of the colloidal particles, the cadence of magnetic toggling, the temperature of the fluid, and other factors will allow researchers and astronauts to further explore the frontiers of self-assembly. Touch the surface of your smartphone again. That's just the beginning.
As you can see, our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. This work off the Earth will lead to a better understanding of the fundamentals of combustion, surface tension, and colloids in the absence of gravity, benefiting us by helping us to make more efficient combustion engines, better portable medical diagnostics, stronger, lighter alloys, medicines with a longer shelf life, and buildings that are more resistant to earthquakes. Research on the International Space Station continues to improve life here on the Earth. Be sure to stay in touch and follow us on Facebook and Twitter for the latest research news, and don't forget to download our app on your mobile device. Until next time, we're working off the Earth for the Earth.